Professor Dave and Chegg here. We now know what entropy is and how it relates to spontaneity, but we also want to be able to describe the entropy change associated with a particular chemical reaction or physical process. Let's get a closer look at this as well.
We know that an increase in entropy is associated with greater dispersal of matter and energy. The way this pertains to chemical reactions is best understood by looking at reactions between gaseous substances. Take, for example, nitrogen and hydrogen reacting to form ammonia. On the left we have 4 moles of particles, and on the right we have only 2. The moles of particles has decreased because molecules are fusing to form the product. This means the particles are less dispersed, so this involves a decrease in entropy and therefore a negative sign for delta S. Fewer molecules means fewer possible configurations for those molecules. Now look instead at this reaction with 4 moles of ammonia and 5 moles of oxygen forming 4 moles of nitrogen monoxide and 6 moles of water, all in the gas phase. What is the sign of the entropy change here? Well, we have 9 moles of particles on the left and 10 on the right, so there is a slight increase in the number of moles of particles and therefore dispersal of matter. Entropy has increased and delta S will be positive. Beyond changes in entropy, we can also assign absolute entropy. This brings us to the third law of thermodynamics. This one deals with the concept of absolute zero. We know that temperature is a measure of available heat energy, which is just a collection of kinetic energies of motion. We know that as the temperature decreases, the internal energy of a system decreases, as does the kinetic energy of each particle. As the temperature becomes very cold, particles slow to a complete stop and even cease to vibrate, and there is no more kinetic energy. No more kinetic energy of motion means no more temperature by any real definition of the term, so we will call this absolute zero. At absolute zero, every substance would be a solid, even things like hydrogen and helium. And one way of summarizing the third law of thermodynamics is by saying that the entropy of any crystalline substance at absolute zero will be equal to zero. This is a necessary consequence of Boltzmann's equation, S equals K times the natural log of W. If there is no kinetic energy, nothing is moving, so there is only one possible microstate that the particles can inhabit. With a value for W equal to 1, the natural log of 1 is 0, so at absolute zero, the entropy of any substance must also be 0. However, absolute zero can never truly be reached, which is communicated in a rephrasing of the third law, which states that it is impossible to lower the temperature of any system to absolute zero in a finite number of steps. This concept allows us to determine standard entropy values for many different substances, and we can use these to calculate the change in entropy for a given reaction by taking the sum of the absolute entropies of the products and subtracting from that the sum of the absolute entropies of the reactants, according to this equation. For example, with this room temperature reaction involving nickel sulfide and oxygen producing sulfur dioxide and nickel oxide, if given these standard entropy values, we simply plug them into the equation like this. Make note that we are multiplying each value by the relevant stoichiometric coefficient. Doing the arithmetic, we get negative 149 joules per Kelvin as the answer.
By looking at entropy changes for different reactions, as well as defining the third law of thermodynamics, we should now have an enhanced understanding of entropy. Professor Dave for Chegg. See you next time.